Section: Introduction. In this section, we discuss ensemble-based exploration, which involves training a diverse group of agents that share data. This method is commonly used in deep reinforcement learning and has shown success in various applications. The main advantage of using a diverse ensemble is that it allows for exploring different strategies simultaneously during training without needing extra data. Additionally, at test time, the learned strategies can be combined to create a more robust overall strategy through methods like voting or averaging. However, despite the benefits of ensemble-based exploration, we believe there is a downside that has not received much attention. Each member of the ensemble mainly learns from data generated by other members rather than from its own interactions with the environment. This type of learning, known as off-policy learning, has been known to be challenging in previous studies. We suspect that this challenge also affects ensemble-based exploration. To investigate this, we conducted experiments using the arcade learning environment and the Jim-Mu-Jo-Ko benchmark with specific algorithms. Our results showed that individual members of a data-sharing ensemble often perform worse than single agents. While combining the ensemble strategies through voting or averaging can sometimes compensate for this performance drop, it is not always effective. This suggests that ensemble-based exploration may have a hidden negative impact that could diminish its advantages, which we refer to as the curse of diversity. We explored various solutions to mitigate this curse but found that they were not consistently successful. Inspired by previous research on the importance of network representations, we introduced a new method called Cross-Ensemble Representation Learning, CERL. This method involves having ensemble members learn each other's value functions as an additional task. Our experiments in different environments showed that CERL can help alleviate the curse of diversity and outperform both single-agent and ensemble-based approaches when combined with policy aggregation. In summary, our contributions include identifying the curse of diversity in ensemble-based exploration, pinpointing off-policy learning challenges as the main cause, and demonstrating the effectiveness of representation learning in mitigating this curse across different control domains. Section Summary. In this section, we introduce the concept of ensemble-based exploration in deep reinforcement learning, where training multiple diverse agents simultaneously offers benefits in both training and testing phases. However, we highlight a previously overlooked downside called the curse of diversity, where individual members of the ensemble can perform poorly compared to single agents due to off-policy learning challenges. To address this issue, we propose Cross-Ensemble Representation Learning, CERL, a novel method that mitigates the curse of diversity by having ensemble members learn each other's value functions as an auxiliary task, leading to improved performance in Atari and Mu-Jo-Ko environments when combined with policy aggregation. Section: The Curse of Diversity. In this section, we present our central finding. We discovered a phenomenon called the curse of diversity in data-sharing ensembles. This curse causes individual ensemble members to struggle with learning from diverse and challenging off-policy data. We demonstrate this phenomenon, identify its cause, and conduct a thorough analysis. We illustrate the curse of diversity using 55 Atari games and 4 Mu-Jo-Ko tasks. Our results reveal that individual ensemble members, like bootstrapped DQN, indiv, perform worse compared to their single-agent counterparts, such as double DQN. Despite being trained on different data distributions, these agents have the same amount of data and network capacity. This underperformance occurs in most Atari games and 3 out of 4 Mu-Jo-Ko tasks, indicating a widespread issue. Interestingly, combining the learned policies at test time significantly boosts performance in many environments, often compensating for the individual policy's performance loss, like in the case of Walker 2D. Our findings challenge previous claims that the success of methods like bootstrapped DQN in some tasks is mainly due to improved exploration. We show that in games where bootstrapped DQN, AGG, outperforms double DQN, bootstrapped DQN, indiv, actually performs much worse. This suggests that the benefits of bootstrapped DQN primarily come from majority voting, rather than exploration. However, this doesn't mean that better exploration from a diverse ensemble isn't valuable. It's just overshadowed by the curse of diversity. Our results also highlight considerations for future ensemble-based exploration applications, especially in scenarios like hyperparameter sweep with ensembles, where individual agents' performance is crucial. Lastly, we see an opportunity for developing improved ensemble algorithms that address the curse of diversity while retaining the ensemble's advantages. To understand why performance degrades in ensembles, we propose 2 reasons: the low proportion of self-generated data for each member and the inefficiency of members to learn from highly off-policy data. We introduce a P% tandem setup to test this hypothesis, where active and passive agents share training data but generate different proportions of it. By comparing setups like double DQN, P% tandem, and bootstrapped DQN, we reveal insights into the impact of data distribution on ensemble performance. Our analysis confirms that the curse of diversity stems from challenges in learning from diverse data. We show a clear link between off-policy learning difficulties in ensemble-based exploration and the observed performance decline. Additionally, we acknowledge the importance of wider state action space coverage in data, which can benefit ensemble learning. Further research is needed to explore the effects of state action space coverage in more depth. Section Summary. In this section, we introduce the concept of the curse of diversity, which refers to the performance degradation in individual ensemble members when faced with challenging off-policy learning from a diverse ensemble. We demonstrate this phenomenon using Atari games and Mu-Jo-Co tasks, highlighting how aggregating learned policies at test time can significantly boost performance. Additionally, we propose a hypothesis to explain this performance degradation, attributing it to the low proportion of self-generated data in shared training data and the inefficiency of individual ensemble members to learn from such off-policy data. Section: Mitigating the Curse of Diversity, Initial Attempts. In this section, we will explore ways to address the issue of diversity in our experiments. We will investigate if increasing the size of the replay buffer can help improve performance by providing better coverage of state action pairs. We will also look into reducing diversity by testing methods such as decreasing the ensemble size and increasing the number of shared layers across the ensemble. Our analysis will focus on how these approaches affect performance and ensemble diversity in different game environments. Additionally, we will introduce a new method called Cross-Ensemble Representation Learning, CERL, that aims to mitigate diversity issues without compromising the benefits of using ensembles. We will explain how CERL works and its potential advantages over traditional network sharing methods. Finally, we will present the results of our experiments to demonstrate the effectiveness of CERL in improving performance and ensemble policies across various tasks. Section Summary. In this section, we explore methods to mitigate the curse of diversity by testing solutions such as larger replay buffers and reducing diversity through techniques like ensemble size reduction and shared layers. While increasing replay buffer capacity can help in some environments, it's not a consistent fix. We introduce Cross-Ensemble Representation Learning, CERL, as a novel method that reduces diversity without compromising the benefits of policy aggregation, showing promising results in improving individual and aggregate policies across various tasks. Section: Related Work. In this section, we discuss ensemble-based exploration in deep reinforcement learning. Many algorithms use multiple agents that share data to explore simultaneously. While most works focus on algorithm design, few address the challenges of learning from off-policy data generated by other agents. One such work highlights the difficulties but requires algorithmic changes for stable learning. Even Q-learning-based methods without explicit off-policy correction can suffer performance degradation with ensemble-based exploration. Some methods use multiple ensemble members per step instead of one per episode, balancing exploration and exploitation. However, these methods are more complex and require further exploration. Ensemble methods in reinforcement learning are also used for robust value estimations and model predictions, but most are single-agent focused. Mutual distillation, where networks share knowledge through collaboration, is common in supervised learning and has been adapted to reinforcement learning. Our method, Collaborative Ensemble Reinforcement Learning, CERL, differs as it does not distill ensemble members' predictions but uses auxiliary tasks to influence representations. Auxiliary tasks have proven effective in reinforcement learning for representation learning. In multi-agent RL, modeling external agents' policies as auxiliary tasks promotes coordination by maximizing mutual action predictability. However, these methods differ from CERL as they predict actions rather than the value functions used in our auxiliary task.